Okay, in this video we are going to learn about transformer, about BERT and GPT and its variations, GPT-2 and GPT-3. We already learned about attention mechanism, and transformer is attention-based model, and BERT and GPT-2 and 3 are transformer-based models. Okay, let's remind what was attention mechanism. Attention mechanism, as we learned in the previous video, in its general form, we have three quantities: Q, which is query, key, and value. Okay, the way that it works is that we have a query and we compare our query with all keys using a similarity measure. And similarity measure could be different things, but in transformer, usually we are using this as a similarity measure, which is basically dot product between query and key with our two vectors, and then divide by the dimensionality of the vector. So in our notation, actually, the dimensionality of vector is P, not D. Okay, that should be P. Okay, and then when we have the similarity, this similarity goes through another layer, which is basically a softmax. We are computing something similar to a probability. I mean, all values are positive and sum to 1 through this softmax. And then we use this softmax as a coefficient of values. Basically, we are computing this quantity, which is softmax will be used as coefficient multiplied to the values, and then that's going to be our attention value. Okay, that was attention mechanism, and we use usually this for self-attention in transformer, but it's general, it's not just for self-attention. It could be used for attention between encoder and decoder, for example. Say, for example, you have a machine translation task, and in this machine translation task, it's not self-attention. Your query is query from decoder when you want to translate a word. So the output word in your decoder basically is your query, and the key and value comes from your encoder. So your input word and in jade position would be your key, and also it would be your value. So you compare your keys in input with the current word in the output, and based on the similarity, you compute a weighted sum of the hidden space of the input values. So it's general, could be used for self-attention, could be used for attention between encoder and decoder. Okay, so let's go through attention again, which we learned in previous lecture, but that's gonna be important for this lecture as well. So I'm gonna write everything in vector and matrix form. So our input, suppose that I show my input with X, it's a vector in D-dimensional space, right? And then I have a key. Key is also a vector, but key is a vector in a different dimensionality, so it's in P-dimensional space. And the way that we compute this vector K is by computing a transformation on X. So WK is a matrix, and WK transpose here is like P by D matrix. So it gives me a P by 1 vector here, which is my key. So query, the same, is a vector in p-dimensional space, and it's going to be computed through a transformation, again with p by d dimension multiplied by x, and the value is also a vector. This vector could be p-dimensional, but could be different from P, could be m-dimensional. Usually in the implementations, existing implementation, m is equal to P, so we use p-dimensional vector, but it doesn't need to be p-dimensional. It could be m-dimensional, different dimension. Key and query should have the same dimension because we want to find, a dot product between them. But value could have any dimension, and the value will be WV transpose X. Okay. So we have different representations of our input in different spaces. In matrix form, you can assume that you have capital X, which is a matrix of all of these vectors, and suppose that you have n of these vectors, so it's going to be d by n, and then you have capital K, which is all of your keys, and you have n keys, so it's p by n, and then you have all of your queries, which is p by n again, and you have all of your values, which is m by n. Okay. Now the way that we compute attention is to compute dot product between Q and the query and key. Okay, and usually we divide this by square root of the dimensionality of the vector. So after computing this, which is now is n by n matrix, we have a softmax layer on this. So in this n by n matrix, it's as if you normalize rows of this matrix such that it sums to 1 and all of them are positive. And then you multiply this by V, which is M. I don't know what happened to. Okay, which is M by N. It's hard to write on this screen. So it's gonna produce the attention for us, attention value, which I show it by Z. And Z is a matrix of M by N. So basically, Z is going to be a matrix of Z1 to Zn. So it's M by N matrix. So that was basically attention, which, as I said, you can compute it for self-attention, or you can compute it for attention between encoder and decoder. So it's not bad to think about the meaning of this dot product. So dot product is a measure of similarity between two vectors, right? So in this particular case, our Q is WQ times X. And I have the transform of that. It's basically X transpose WQ, right? And K is WK X, which is N by N matrix. So if I don't have this W's here, X transpose X is just a linear kernel over X, which shows the similarity between pairs in X. Also, if this WQ and WK are identical, again, that's going to be a kernel. But they're not identical, they're different. So it's not like a kernel exactly, because kernel shows similarity between pairs. It's like one-dimensional, one-directional similarity. So if I have n by n, it's not symmetric anymore. So the similarity between x1 and x2 is not the same as similarity between x2 and x1. You know, it's different. But still, it's a measure of similarity, but it's one-dimensional similarity. So we basically projected x in different spaces, and then we computed the similarity between them, and it's not symmetric. It's like divergence, not this. The difference between divergence and distance. It's one direction. Okay, now that we know attention, let's look at transformer. There was a paper in 2017, Attention is All You Need, quite appealing title for the paper, which introduced transformer and was a breakthrough in deep learning, and especially in natural language processing. And not only natural language processing, transformer has been used in other areas as well. But originally it was used for machine translation, and then it is building block for many state-of-the-art models like BERT and GPT-2 and GPT-3 that we are going to discuss in this lecture. So this figure seems to be complicated at the first glance, but I'm going to explain a component of this step by step, and it's not really complicated when we explain them. So it has two parts. It has this part, which is encoder. This is encoder, and has this part, which is a decoder. Okay. So let's look at each part separately. The encoder, the first part. So the encoder has different component, but the most important component here is this layer, which is self-attention, and this one, which is feed-forward neural network. Okay. So basically, here I have a self-attention layer, and then the next layer is feed-forward. But something important to consider is that this feed-forward, basically, self-attention, basically here I have different positions, like I have x1 to xn coming inside the self-attention, and I have z as the output in different positions, right? So important point is that there are many feed-forward neural network, and each position goes to a feed-forward neural network separately. These neural networks are identical. They're all the same. But each position separately goes through a feed-forward neural network. So that's the two important layers that we have here. Okay, so the output here would be Z. Say the output of neural network, I call it R. Okay. Z goes inside a feed-forward neural network, and the output, I call it R. Okay, there is this notation here. This basically means that this block, the whole block, which is a self-attention and feed-forward neural network, will be repeated n times. And in the implementation of transforming, this n is 6. So these are hyperparameters of the model. There is no magic about the number 6. It just turned out that through trial and error, they found out that 6 works the best in the setting that they had, and they kept it 6. So this block, which is self-attention and feed forward, will be repeated 6 times. Okay. Okay. What else do we have here? We have this. Residual connection. Okay. So these three actually are key, query, and value, which goes inside the self-attention. And then I have this residual. So basically this residual means that here it's not Z that will be passed to the neural network. It is basically Z plus X, which will be passed through neural network. So this residual add X, the input of the self-attention, to the output X. To output Z. And then I have this layer, which is add and norm. So after, adding basically this layer, adding Z and X, and then normalize it. And then this after normalization will goes to the feed-forward neural network, and I have another residual layer connection here. So basically it means that, this is the first one, and here means whatever I have here, then this Z plus X normalized will be added to the output. So R plus Z plus X normalized will be normalized again. And then that's going to be the output of the first block of this attention. And this exact same thing will be repeated 6 times. Okay, you may wonder, why do we add X to Z here? So we want to keep the identity of the input. So X was basically a representation of, say, a word, a token, right? And this X, which was the representation of our token, when goes through self-attention and produce Z, Z has to do with, Z is weighted sum of values of this representation. So it has to do with it is a representation of the original token that we had, but to keep the identity of the original representation, which is add the original representation to Z and then normalize. Okay, there is another thing here, which is this position encoding, and position encoding we'll talk about later. You learned about word2vec and glove, and you know that using word2vec or glove, you can represent a word by a vector, a fixed vector, and then you can basically, when you have a sentence or a sequence of words, you can have different fixed vectors for each of them using word2vec. So in existing, in the most recent models, we don't do that. We don't use a fixed representation. Usually we have an embedding layer, and through this embedding layer, we learn a representation for each word at the same time that we learn everything else. So it's end-to-end, and we don't need to use a dictionary of word2vec or glove for word representation. Okay. So I think the only component that we need to talk about later on is this position embedding, position encoding, sorry. Okay. So I have to add something to what I just said, that I told you that we have basically self-attention layer, and then we have feed-forward layer. Now I want to add to this that this self-attention, I want to add to this that this self-attention here is not only one self-attention, there's many, okay? So basically I'm gonna have another layer of self-attention. So I have 8 of them, okay? So basically I have, in fact, in the implementation of transformer, we have 6 of them. That's why it's called multi-head attention. So how does this work? You know, for attention, we know that we have query, we have value, and we have queue, and we know each one is basically a linear transformation of the input. For example, K is going to be like WK transpose X, right? Now, suppose that you have 6 of them. So you have W1K transpose X, which gives you 1 key, and then you have another one. It's different from the first one. And you have the third one, and so on and so forth. You have 6 of them. So you basically compute 6 keys, and you compute 6 queries, and you compute 6 values. And each of them separately produce a Z, right? So we learned that they produce a Z as basically V times softmax of Q transpose K divided by P. So instead of having one of them, I have, sorry, I said 6, no, it's 8 actually. In the implementation, it's 8. But as I said, it's like hyperparameter, it's not important. But in all attention is all you need paper, there's 8 of them, 8 heads. So basically, instead of having one Z, you have 8 Zs. For basically for each position, I have 8 of these Zs, not only one. Before I go to the neural network, to feed-forward neural network. So feed-forward neural network expect a vector, not 8 of them. So what I'm going to do is that basically, you know, I have 8 Zs, and then what I'm going to do is to concatenate all of these 8s, right? And then remember the dimensionality of Z was m by 1, so it is basically 8 times m by 1 when you concatenate them. Now you multiply this by a new matrix WO, right? And it's going to give you a new Z. Okay. So that's basically what I wrote here. So multi-head attention means that you concat the output of different heads, and then you multiply by a linear transformation. So you reduce the dimensionality to, say, m by n. Okay, so that's what the neural network expect to see. So these are basically concatenation step, and this is the linear, means that you multiply this this concatenation by this new matrix. And we have to learn all of these matrices. You know, we have to learn WK, WQ, WV, 8 of them for each position. And then we have to learn this W null. So to recap, in encoder, I have basically self-attention, and then self-attention, you know that it comes with some details like residual and normalization, and then output after this go to a feed forward, and then also residual. But now I just added that I have 8 of these, you know, and this 8 of these self-attention will be concatenated and multiplied by this linear attention, and then go to the feed-forward neural network. Okay. So, and now this module, which is, oh, what happened actually? This module, I just wanted to tell you that this module will be repeated six times. You know, the module of basically multi-head attention, and then feed forward will be repeated 6 times, and then everything together, all of this 6 together makes encoder. So to visualize what's happening after, you know, doing this attention many times, you know, like 6 times, and with multi-head attention, you know, I borrowed this a couple of figures from different papers and blogs, and this is from J. LMR. It shows what's happening, for example, in layer 5 when you have this sentence. The sentence is, the animal didn't cross the street because it was too tired. So you may think that when you read this sentence, you may think, okay, when the sentence says it refers to animal, but it refers to street. The animal didn't cross the street because it was too tired. Who was too tired? Street was too tired, or animal was too tired? So when you do self-attention, you know, the attention between the sentence and itself, you can see that the word it in layer 5 attended to the animal the most. You know, the thickness of these connections shows the coefficient of the attention. So when I want to compute the value for it, it's a linear sum of some values of all of these words, right? The linear sum of all of these words. And you can see that the coefficient of the animal is larger than others, okay? So basically, this layer 5, what the model learned is that this it refers to the animal, not refers to street. There are many things that will be learned. That's another example. This figure is also not mine. I borrowed this from Jessica. Okay, so this is another example. In this example, you can see we have this sentence, the girl and the boy walked home. That's the first sentence. And there's second sentence start with she. So the girl and the boy walked home. In the next sentence, you would say she. Okay. If you look at the self-attention, you can see that she basically refers to the girl. Okay. So it has high coefficient. But if the next sentence starts with he, then he will refer to the boy, not the girl. Okay. So basically, it's called a co-reference resolution, you know, who she refers to, who he refers to. Or if you have in the context, you know, another sentence that, you know, basically this she, you have, you know, when you say she, then you basically you have Alice came up to Bob. she refers to Alice and talking about Alice who came up to Bob. But if there's he will refer to Bob, you know. So there are many useful and interesting things that this attention mechanism can learn through this encoder. In different layers of encoder, we have this type of information, which is going to be quite useful and important for uh, basically natural language processing and understanding language. Okay, let's look at the transformer again. So transformer had two parts, encoder and decoder, and we learned about encoder. Now this is basically the decoder part of the transformer that now we have to learn about. So transformer is similar to the decoder of the transformer is similar to the encoder with some differences. So remember that in encoder we had two main layer. One of them was self-attention, the other one was feed-forward neural network. Now we have three. The first one, in encoder it was self-attention. Now it is masked self-attention. And what's the difference between masked self-attention and self-attention? Basically, masked self-attention mask every word on the right, attend only to the word on the left. So this is decoder. Decoder would we want decoder to generate a new word for us, generate a new character for us. Okay, so generate a new text for us. When you are generating a text, I am a so when I'm when I want to basically generate this new word, I don't need to attend to words which comes after this. I just need to attend to the words which comes before this, to the left, not to the right. So what I had, what I said so far, I am a. So I'm just need to attend to this word. So that's what mask self-attention does. Mask self-attention basically mask everything which comes after. So look at the words before. So that's the difference between mask self-attention and self-attention. So in this layer, mask self-attention, we're just looking at the previous one. And again, this is multi-head, similar to self-attention, which was multi-head. This is also multi-head, so we have 8 of them. Okay. So we have another layer here, which is basically this one. Multi-head attention. We didn't have this one before, and I'm going to explain what that is. And then we have feed forward, and we had feed forward before. Okay, so we had this feed forward before, and we had this layer with the exception that it attends to the left, not to the right. So what is this new layer here? Multi-head attention. This new layer, multi-head attention, mimic the type of attention that we had in sequence-to-sequence model. So it's not self-attention, it's attention between encoder and decoder. Okay, so here actually is your query. And these two are key and value. So key and value comes from encoder. But query comes from decoder. So I want to generate a new word. So that's my query. Okay. Now key and value comes from the encoder. So which part of the encoder is most useful for me? My query compare itself with all of the keys that I have from encoder, find similarity, find softmax, make a weighted sum of those values, and then this weighted sum of those values would be the value that my encoder should attend to, should pay attention to. So basically this is going to be an attention, not self-attention, cross-attention between encoder and decoder. So that's about this new values, right? And then feed forward is the same as what we had in encoder. So each position has separate feed forward, and they're identical. And also similar to what we had in encoder, here also we have this residual. We have this residuals. Where is it? Here we have this residual, exactly the same as residual that we had before in encoder. So add the value, add x to z. So I have z here, add x to z, and then normalize it, and then pass through multi-head attention, and so on and so forth. So, so this should be clear now. All components that we have this in encoder, and again we repeat this 6 times. So we have like 8 of these multi-head attentions, 8 of them, and then will be concatenated, will be multiplied to a W, go to lower dimensional space, then pass through a feed forward, and then the output of this comes to another linear and a softmax. So the output basically will be multiplied to a matrix, which this matrix, this transformation, make the dimensionality of the output matrix the same as the dimensionality of our vocabulary size. Say, for example, I have 50,000, say 50,000 vocabulary that I want to choose from. So this becomes, the size of my vocabulary, and the softmax goes after, comes, on the top of that. So I have a probability over all possible vocabulary, and probability somewhere is higher than others. So I'm going to choose this word, and that's going to be my output word, the word that this decoder will generate. So still we don't know about position encoding. Okay, so to recap, decoder has mask self-attention, and it has encoder-decoder layer, which this encoder-decoder helps decoder emphasize on relevant part of the input. Okay, and again, the same feed-forward neural network will be applied to each position. Okay, so what about positional embedding that I kept promising that I will explain what positional embedding is. So, so far, our model has no sense of the sequence, right? So, the first word has a vector representation, the second word has a vector representation, and so on and so forth. So if I have a sentence, and in this sentence for each word, if I have a vector representation, and I want to represent the whole sentence, say for example, I add them up. We don't add them up here, but just as an example. So if I add them up, any basically permutation of these vectors will result the same vector. Order doesn't matter, right? So I don't want this. I want to have I want my model has a sense of order. If word I comes at the beginning of the sentence, it's different from the I which comes at the middle of the sentence. So this should be different. If I scramble the word, I shouldn't get the same representation as the whole sentence. I should get a different representation. So that's the problem. The problem is that there is no sense, we don't have convolution, we don't have reference, we don't have any way to take care of sequence of the words here. So what can we do? The solution that has been proposed in this paper, attention is all you need, transformer model, the solution is add a vector to word representation that we had. I had this X as word representation. Let's add it with another vector. So this is my basically word representation. I'm going to add this to another vector to this. And the second vector somehow capture the position. Okay. So what would be the simplest thing that I can use to capture the position? There are many different solutions. For example, I can have like one hot vector, for position 1, this is position 1, right? And for position 2, this is position 2, and so on and so forth. So I just need to come up with a way that a vector capture the position, and whatever this representation of the position is, I'm going to add it to my word representation. So the solution that they came up with is not the only possible solution, but it's a solution that works, and it's a wise solution, is to define a continuous function which captures the position. So they defined two periodic functions, a sine and a cosine. And this is my position, and this is the dimensionality of the vector. So basically, say for example, at position 1, if I set I equal to 0, 2 times 0 plus 1 would be 1. So I have a vector. The value of this periodic function would be the value of my first entry of this vector, right? Because I is equal to 0. And I is equal to 0 here, this is 0. So I don't care about it. So if I is equal to 1 for the first position, this is still 1. For the first position, if I is equal to 1, 2 i's would be 2, then the output of the sine function would be my second value of this position vector, and 2i plus 1 would be 3. That would be the third position of my vector, and then I equal to 2 give me basically these two values, and so on and so forth. Okay, so basically I can have my vectors were p-dimensional, and I can produce some p-dimensional vectors which captures the positions, and then I can add this to my representation. Okay, so how come these two vectors capture the position? Let's take a closer look. I have two functions, cosine and sine. Let's look at the cosine. This cosine function, if I is equal to 0 for different positions, is a periodic function like this. Okay, so there's my x-axis here is positions, and I fix the dimensionality. I is equal to 0. So basically here, since I equal to 0, I'm only talking about the first value of position vectors. So the first value of positions vectors across different positions can be captured by this function. So at position 10, that's the value of my vector. And at position 20, that's the value of my vector. Okay. So I had another function as well, which was a sine function. And the red one is sine function, So, and the sine function, basically the cosine functions captures odd values, and the sine function captures the even values. Okay. And then I can generate as many dimension as I like, like a p-dimensional vector this way, and then add it up to the representation of the word that I have. To have a better idea, what I showed you was for I equal to 0. If, say, I is equal to 50, these are the functions. It's a periodic function with different frequency. So I will, when I go to higher dimension of this vector, the frequency is low. The function is basically wider. Okay. So that was for the case that I fixed dimension of the vector, and I showed you the function across position. But if I fix position and show you the behavior of the function across different dimension, that's how it look like. For position 1, for position, sorry, this is not position 1. For position 1, for the first word, say for example, for the first word, these are the values which is going to be generated by cosine function. Cosine function generate odd numbers, odd dimensions. Okay. So these are the values. So for basically, that's what is in dimension, in 100. And this is what we have in 200, Okay. So in this case, for example, you see after 100, we have a constant value of 1. And this is in position 2, and this is in position 50, in position 50. You can see that, the last part of the vector is all 1, So basically, you can imagine that, it is similar to a one-hot vector that has like zeros, 1, 1, 1, 1, 1 for the first position, and then has like 0, 1, 1, 1, 1, 1. And it's not, in fact, between 0 and 1, it's between 0 and -1. It's like juggling and then becomes 1, 1, 1, 1. It's sort of one hot vector, but it's continuous. That's a good point about it. Okay, when you put everything together, that's how it looks like. Each row here, each row is a position vector, each row is a position vector for one position. So that's for first position, like 1, 0, 0, 1, 0, 1, 0, 1, 0 up to end. And this is for the second position, and this is for the third position, and so on and so forth. So you have position vectors, and you're going to add these position vectors to your input. So now, basically, x plus position vector is a new vector which has a sense of the position as well. Okay, and that's what's going to be passed to transformer. So far when we talked about transformer, we just talked about x, but in reality, it's not x that will be passed to transformer to different layers of like self-attention, so on and so forth. X plus this position vector is going to be passed through self-attention or mask self-attention, and so far and so forth. Okay. Now we know about attention and we know about transformer, that, as I told you, transformer is a breakthrough, and almost all natural language processing models have been built using transformer after 2017. So there are two interesting models, state-of-the-art model in natural language processing that basically all of the natural language processing is state of the art using these two models. One of them is GPT, introduced first in this paper in 2018, improving language understanding by generative pre-training. And this generative pre-training, in short, is GPT, and these are the authors. And OpenAI introduced this model. And there was another paper in 2018, BERT, pre-trained of deep bidirectional transformers for language understanding and bidirectional transformer for language representation. Basically, is a model which is called BERT. And these are the authors from Google. Okay, what is BERT and what is GPT-2? GPT-2 is basically a stack of decoders of a transformer, and BERT is stack of encoder of transformer. So the transformer that we learned had two parts, had encoder and had decoder, right? Now, suppose that I just use encoder and I use many of them, many of these encoder. So this is BERT. This is BERT. Or suppose that I use decoder and I use many of these decoders. Okay. Stack of many decoders. This is GPT. Okay. In the decoder, if you remember, we had this mask self-attention. We had a layer which was taking care of, it was basically cross attention between encoder and decoder, and then we had feed-forward neural network. So when you stack only decoders together, you don't have any encoder, you don't need this layer. So basically GPT is layers of decoder without this layer of cross attention between encoder and decoder. So it's only masked attention and feed forward. Okay, many of them becomes GPT. Okay, so you have stack of encoders only, right? When you had transformer, you had encoder and you had decoder. You had in transformer, I had encoder and I had decoder. And I had a task, my task, say, for example, was language translation. The input was English, the output supposed to be in French. So I can, define an objective function, minimize for this parallel data set that I have between English and French. But if I have only encoders and I have many of them, what would be the task that I want to do with this encoder? How can I make a language model just by encoders? So here is actually pretty interesting idea that they had, that I can define a task here, and the task is that if I mask a word in the input, I want my model to predict that word. So I have a sentence, I'm going to mask a word here, okay, and then pass everything else to my stack of encoders. So the output, I want to define my objective function in a way that my output would be this word which has been masked. Okay, and then I mask another word. And then I want my model to predict that word. So What's interesting about this is that I can do this training completely unsupervised. I don't need label data. And there are massive amount of data on the internet. So basically, I can train a masked language model by masking some of the words and getting a stack of encoder to predict that. Okay. So what is this good for? So the output of this BERT is going to give me a representation of the words, afterward, which this representation of the words is context-based. We learned about word2vec, we learned about glove, and word2vec give you a fixed representation for a word. Word bank has a representation, a fixed representation. No matter what your context is, sometimes I'm talking about bank of a river. Sometimes I'm talking about bank that, I go to cash my check in it, right? So they have different meaning, but in word2vec, there is one single representation for this word. But here I can have a context-based representation, basically BERT look at the whole context and produce a representation for each word. To give you more details, actually, BERT gives you a representation for each token that you have. It also produces another output, and this output roughly can be seen as a representation of the whole sentence, roughly. It's not a very good representation of the whole sentence, but it can be used as a representation of whole sentence. If, for example, you have a task of spam detection, you have a sentence here, and you want to know if this sentence is a spam, or this email is a spam or is not a spam, you can just use this one and put a classifier on the top of this. And this classifier could be quite simple, could be 1 layer, 2 layers neural network, and they have shown that with simple classifier you can do state of the art, because this representation is pretty rich representation. So using this, BERT is now a pre-trained model. You don't need to train it yourself. In fact, it's quite a large model and you cannot train it easily. So they already train it with a huge amount of data, and the pre-trained weights exist. Now, when you want to build a natural language model, you just take BERT as a block, which is pre-trained. The weights is noun. But what BERT does is to produce a pretty rich and interesting representation of your tokens, your words, right? And then you add, a layer, 2 layers, whatever, on the top of BERT to build your natural language model, which is whatever it is. It's, sentiment analysis, it's spam detection, or whatever it is. Quite interesting. You don't need to train it again. It has been already trained, and you just pass your words inside, and it gives you pretty rich representation of the word, and you're going to use it for your task. Okay, besides what I said, which is basically you're masking 15% of a part of the word, which is in their implementation is 15% of the word, they added another task to understand the relation between sentence better. And the second task that also can be done in an unsupervised manner is to find out if a sentence is the sentence which comes after another sentence or not. Say, for example, you're parsing sentence B, and you're asking this question, is sentence B, is the sentence which comes after A or not? Okay, so you have binary answer, yes or no. So two tasks, you have this stack of encoders. The first task is you wanted to predict, mask word. Another task that you want this model to do is that to realize if B comes after A or it doesn't. Okay, so so it's gonna learn the relation between sentence better. So it's pre-trained and it learned bidirectional representations from unlabeled text. Basically, it's jointly conditioning on both left and right context, because you have this sentence and you're masking one. It's conditions on the left and conditions on the right. Uh, So I told you that BERT is pre-trained and you can use it as a building block of a natural language processing model, but you can fine-tune it as well. And usually that's the case, that we not only we add, another part to this, which we have to train this, we can also fine-tune the weights of BERTs for a couple of epochs. And almost all of the state-of-the-art natural language processing today has been built using either BERT or GPT that I'm going to explain. BERT is a large model. You remember that transformer had 6 encoder layer and 8 attention head, and the hidden layer of the feed forward was that we had in transformer is 512. BERT, the large BERT, actually, when we say BERT, we usually mean large BERT. Instead of 6 encoder layer, has 24 encoder layers. And instead of 8 attention head, has 16 attention head. And the dimensionality of feed forward is 1024 instead of 512. There is a smaller size for BERT, which is called basic BERT, and it's 12 encoder layer and 12 attention head, and the dimensionality is 768. So there are many distilled version of BERT, tiny BERT, small BERT, Roberta, because these models are quite large. It's not easy to put it in like edge devices, because the model is huge and you can't put it in edge devices. You can't put it in a phone, for example, or a small device that you have, because it's going to take lots of memory. So they came up with distilled variations of BERT, and there are many of them, like as I said, Roberta and tiny BERT and small BERT and so on and so forth. Okay, what about GPT? So BERT was a stack of encoders. GPT is a stack of decoders, with the exception that I told you. Decoders has 3 layers, mask self-attention, cross attention between decoder and encoder, and feed forward. So get rid of this layer. So just masked self-attention and feed forward, and then stack them together, many of them, and this is GPT. So since it's mask, it conditions only, when you have a sentence, it conditions only on the, and say I'm talking about this word, condition only on the left side, not on the right side. Okay, so the objective for BERT was to mask a word and predict that word. So it was conditioning both on left and right. The objective for GPT is to predict the next word. You know, I have this sequence of words up to this point, and I want to predict next word. So given the words that I have seen so far, what would be this next word? Okay, so at each time step, I want to predict a new word. And then this new word will be added to the sequence. I assume that I have all of these. So what would be the next word? And then when I predicted this, I will add this to the sequence, and I'm going to predict the next one, and so on and so forth. So it's still, again, you know, I don't need labeled data. I can train this GPT using unlabeled data. And again, I have huge amount of unlabeled data, so I can train a huge model. A successor to GPT is GPT-2 and GPT-3. Okay, which we will talk about them more. In GPT-2, you know, these are all about GPT-2. In GPT-2, the model has 1.5 billion parameters. Quite huge model, 1.5 billion parameters, the GPT-2. So it has been trained with 40 gigabytes of data and 8 million web pages. As I said, GPT-2 is a quite large model, but it comes in different variations, different size. Basically, the number of decoder, it's a stack of decoder, the number of decoder is less or more. So original is 1.5 billion parameters, as I said, but there are variations in the small, medium, large, X large, and distilled GPT-2, which is smaller than others. This is an example text that has been generated by GPT-2. Quite impressive. That the top part is a part that has been written by a human. In a shocking finding, scientists discovered a herd of unicorns living in a remote, previously unexplored valley in the Andes Mountains. Even more surprising to the researchers was the fact that the unicorns spoke perfect English. So this is written by a human. This is the input to the GPT-2, and GPT-2 tries to predict the next word, and the next word would be D. So this D will be added to the sequence, and GPT-2 tries to predict the word after, which is scientist. So it came up with this text. The scientists named the population after their distinctive horn, Ovid's unicorn. These four horned silver-white unicorns were previously unknown to science, and up to the end, GPT-2 even came up with some names: Dr. George Praz and University of La Paz. These are all false facts. You know, there is no such a scientist in such a university, and GPT just coined them. 5 had 1.5 million parameters, but GPT-3 has 175 billion parameters. 175 billion parameters, just remember that we have only 86 billion, approximately 86 billion neurons. It has 175 billion parameters. It's the largest deep neural network that has been built so far. Before that, the largest was a model by Microsoft, which had 17 billion parameters, but this one has 175 and has been introduced only 3 months ago. So it's quite new model. Still, it's a language model with the same logic that I told you. It only has more layers and more heads, you know, and you know, that's the main difference between different versions of GPT. It just becomes larger by adding more and more and more layers to it. So you can do many different things. You can create fictions, you can write poem, chat, which is pretty similar to human. And more interestingly, you can write computer codes, because computer codes is language, right? So you can basically write computer codes. And you can summarize a text. You can answer questions, many different things. These are from the demos that they showed. You can design an application, when someone writes the description of the application and it writes codes for it. You can think that the input, it's language to language, right? Because the output is also language, but language in a programming language, uh, can write codes for an application. It can fill a table, for example. You have a spreadsheet and you have only titles of this spreadsheet, and it can guess that when you say company, what do you mean by company? Put some name of companies here, year founded, can add, basically have a sense of what you mean by the title that you had here. So it should be a number, and it should be a meaningful number. And can answer your questions. You can go to a web page like Wikipedia, type a question, and it goes to pages and find, the paragraph which answer your question if it exists in that page. The API of this GPT-3 is public, but I think there is a waiting list now to use this API, and it's impressive model, but can basically appreciate the fact that, this comes from having a very large model with many parameters and many texts. In a sense, the model have been memorized everything, but memorized in a pretty wise way, It's not just memorizing like a lookup table. It's pretty wise way of memorizing things, like maybe a soft lookup table, not just a lookup table. But the reason that, one of the reason that the larger the better is that, it has the capacity of memorizing everything, memorizing all of these codes, that when you describe something and you want the model to draw a circle or triangle and so on and so forth, it has seen something similar in the training set that it had, and can understand the relation between what you are requesting and the corresponding code.